In this video, I'll be demonstrating this amazing sound chip that even Mr. T will be proud of. So a few months back, I got this in the mail. I don't know who it came from, and I had no idea what it was. I discovered it's the SN76489 Digital Complex Sound Generator. It's a programmable sound generator chip from Texas Instrument. It was actually used in the 80s in various gaming consoles to produce sound and music, like the TI-99, BBC Micro, and Tandy 1000. So inside this chip is actually 3 square wave tone generators that can produce sound and noise, where you can generate white noise. And for something this small, it's actually quite a powerful chip and can generate some quite amazing music and sound. So in this video, I'll be connecting this up to a Z80 microprocessor, programming the chip, getting it to play various notes and sounds, and ultimately being able to stream music from my computer via the serial port to this chip to play some awesome tunes. So the first thing I need to do is get this chip connected up to a microprocessor and get it to play some tunes. So the SN76489 only has 16 pins, and most of them are data pins, so it's pretty straightforward connecting this to any microcomputer or parallel port or even an Arduino, but for the Z80, relatively straightforward to connect to. So power and ground just goes for 5 volts and ground, pin 16 and 8. Pin 14 is the clock pin. That can go directly to your CPU clock, but the clock actually determines the frequency of the tones that it produces, so it can be external. A clock rate between 4 megahertz and 2 megahertz kind of suits really well. The next 3 pins, 4, 5, and 6, they just directly connect to the Z80. Output enable is like a chip enable. Well, that's the output port, something the IORQ will trigger to set low. I connected to port 7 on my tech computer. Could be on any port that you decide. The right enable, active low, that's just connected directly to the right pin on the CPU. And it does take 32 clock cycles to actually produce the tone. It needs to pause the CPU for a brief moment. And that's the ready line, pin 4. That's an output, and that's connected directly to the wait line of the CPU. Audio out, that just goes directly to an amplifier. You only get a very small signal out of the chip. I'm going to use an LM386, but you can use something similar. Pin 9 is not connected. And then the data pins, well, they just connect directly across to the data bus. And that's it. Well, it's not actually it. If you look really closely at the data sheet of how you send data to this chip, on the left-hand side usually we'll represent that as the high bit or bit 7, but no, they've somehow decided that we should set it to bit 0. So actually the least significant bit is on the left-hand side, and the most significant bit is the right. So connecting the data lines directly together isn't going to work. To fix this, all you need to do is to swap the lines around. So D0 goes to D7, D1 to D6, etc. So this is very important, otherwise you're going to get some weird sounding notes. And that's our simple connection. Have you been dreaming of that electronic project and want to make it a reality? Just like my ultimate expansion board for the Tech 1F. Well, head over to PCBWay to make your dreams come true. PCBWay are the leading printed circuit board manufacturer. They make high-quality multi-layer boards with a 24-hour production time. Just enter the board dimensions and upload your Gerber file, and that's it. Once posted, a neat box will arrive with your well-packed goodies. Just look at the quality of this board. They also do PC board assembly, CNC machining, and 3D printing. You can even order user project boards directly from their website. For $5 off your first order, click on the link below. PCBWay, prototype the easy way. So this little board here is great for testing the chip, but it really needs an amplifier as well. So I've gone and created my own board, and here is my own board. Thank you to PCBWay for producing this beautiful board. It's actually in 3 components. You've got the SN76489 chip and the connectors to the computer, or the external connectors here. This section here is amplifier, I am using an LM386. Now, it's not the best amplifier chip. You can get a lot of feedback and noise, but I believe the circuit I've created is the best in terms of reducing the noise quality. If you don't want an amplifier here, you can actually just connect to an external amplifier connection here. And lastly, just to make things a bit more interesting, I'm connecting it up to also an LM3915. Now, what's that chip? That's an analog VU meter chip, which is designed to visually represent the sound by various LEDs. It's going to look really cool when I finally get this built. So let's get the basics started, get this connected up to the computer and the SN76489 chip installed. If you've been watching my channel, you'll be familiar with this Tech1F Talking Electronics Z80 single board computer. And for this simple setup, I've just got the sound chip only and to an external amplifier. Now, these amplifiers are pretty cheap, only a couple dollars, but they're pretty ordinary. For now, let's see what it does do. I'm just going to turn it on. I don't know if you can hear that, but it's already producing some sort of sound, some sort of noise sound. Just putting power to this chip just produces some random tone. So we've got to figure out how to turn the volume down or turn it off. So let's see how we can do that. So the chip produces tones at a certain frequency. How do we work out that frequency? Well, they actually give you a formula. And here it is, frequency equals n divided by 32 times little n. But what are those n's? Well, big N is the input clock rate into the chip, and little n is this 10-bit binary number. That 10-bit binary number is the actual one we need to send to the chip to produce the frequency. But it's hidden into that little formula on the right. So let's fix this up and rearrange the formula. And we get n on the left-hand side equals big N divided by 32 times frequency. Now, 32 is actually the number of clock cycles the chip actually needs to generate the sound. So let's say we want to produce a 500 hertz square wave tone, and I'm using a clock of 4 megahertz. 4 million divided by 32 times 500, that gives us 250 decimal, or FA hex, or more importantly, the 10-bit number in binary is 0011111010. So how do we use that 10-bit number to produce a square wave of 500 hertz? Well, we send it to the chip, but we need 2 bytes. And this is the structure. The first byte, bit 7, needs to be always 1, and then the next 2 bits are the channels or the tone. So tone 0, 1, and 2. I'll call it channel 1, 2, and 3. They're the next 2 bits. The 4th bit needs to be always 0. That's a special tone or volume bit. And then we use that 10-bit number on the rest of the byte and the second byte. So here's our 10-bit number. Byte number 1 starts with a 1. Let's say we want to send it to channel 1 or tone 0, 0, 0, and then 0. And then we append the last 4 bits of the 10-bit number to byte 1. Byte 2 starts with 0. The next bit is irrelevant, so let's put that as 0. And then we just append the rest of the number to the byte, and then we've got 2 bytes. They are 8A and OF in hex. Once the tone is sent to the chip, it just plays forever until another tone replaces it, or you change the volume. They use the word attenuator. It's a bit technical for me. I just use the word volume. Easy to understand. And it's only 1 byte to send. It's exactly the same first 4 bits, 1 and then the channels, but the 4th bit has to be 1. That's the volume bit. And then we send 4 bits of data. If it's zeros, it's the loudest volume. And if they're all 1, it's the lowest volume, which is actually mute. So to turn the volume off, I'm just going to use this simple Z80 code that uses OTIR to send 4 bytes out to the chip. So BC set to 04, so 4 bytes, and 07 is the port, so I'm using port 7. And then load HL with the address of the 4 bytes, and then use OTIR. And we don't want to execute anymore, so just halt. And now the 4 bytes. To mute the full tone, we put an F on the end, so it's 9F, BF, DF, and FF. Reset, go. It's gone quiet now. This is what we want. Great. That's working. Let's see how we can play a tone now. Alright, so that 500 hertz square wave, we need to send 2 bytes, 8A and OF. Let's do that now. So 3E, load the register A with 8A, output it to port 7, load the register A again with OF, output it to port 7, D307, and then we need to set the volume up so we can hear the tone. So load the register A with 90, D307 port A, 76 to halt. Reset it and hit go. And there you have it. There's our 500 Hertz square wave tone. Now, this is all great, playing one little tones at a time, but what actually is 500 Hertz? I mean, I don't know what that actually is. Is that like a particular note on a piano? We really need to map the frequencies to actual notes so we can play some actual music. So let's see if there's a way to do that. For me, who has no music experience, I've always wanted to play in a band, but I can't sing or play an instrument. I've had to nerd my way through this and had to learn how to read music from a music sheet. So here's a 1-minute overview of how to read some music. Because if you want to program it to actually play some songs, you kind of got to understand what a note means and how long the note should go for. You probably would have seen something like this, a bunch of lines with some filled in circles with lines on it. Well, they're notes, and the lines are called the stave. You've got two staves usually, a treble and a bass. Basically, treble's higher, bass is lower. And there's a note right in the middle called middle C. And they use the A to G to represent notes. And they go kind of, fortunately, in sequential order. And middle C is actually important because that's on the 4th octave. So C4 goes upwards to D, E, F, and then it goes to A4, B4, and then C5, and that changes octave, and also in the other direction. And those numbers, C4, D5, A4, etc., is what I'll be using to program this chip. What about those note shapes? Well, that determines how long you hold the note for. So just a hollow circle is 4 beats. A hollow circle with a line is 2 beats, called minim. A crotchet is a filled circle, and that represents 1 beat. Quaver, similar looking but with a little tail on the end, half a beat, and a semiquaver, two tails, quarter of a beat. And again, those words, minim, crotchet, is what I'll be using to determine how long to hold those notes for. So how do we set up the chip to produce actual tones that, someone who plays a guitar can actually understand? Fortunately, there's another formula to use. Again, they're all pretty simple formulas. The formula I'm going to use is 440 times 2 to the power of index divided by 12. Now, what is an index? Well, for representing A4, which is A on the 4th octave, put that as 0. We can then determine all the other notes. And using the original formula to put into our chip, now we've got the frequency. Once we know the index, we can get our 10-bit number and then produce a whole range of notes to use. And here's a little table for some of the notes. So A4 is right in the middle. If you look at the index column, minus goes to A4 flat, G4 minus 2, and positive C5 is 3. Put that into the first formula, you get the frequency in hertz. Put the frequency in hertz into the second formula, we get the N number, and that's in hexadecimal. And in the binary format, a 10-bit binary number, and that's the number we'll use to send to the chip to produce the exact tone. So if we want C5 exactly, we would send 00EE to the chip, or that 10-bit number that it represents. So here is the full range of notes that the chip will accept and play actual real notes. This is based off those two formulas. I have slightly rearranged these values to make it slightly easier to put into the chip with the 2 bytes. And I've got a note about what to do here. So what do I do with these values? Well, I've created a library which can assist in playing all sorts of different tunes. So some functions are to play a tune with multiple channels or a single channel, play some VGM files, which I'll explain later, and also have the keyboard as a piano. Here's an example of playing just one note only. All you need is a string of note data or song data. You have the note type, so C5, and the length of that note, crotchet. C5 quaver, A4 crotchet, etc. This is using the play tune single channel example. So let's hear this song. Alright, I've updated the board now. I've put the amplifier components onto the board, taken away this crappy cheap amplifier to use a better one, connected the speaker directly to the screw terminal, or you also got an optional audio jack there. It is only mono because we've only got one chip. So this is the first tune that I've got to demonstrate. This is called Summer Garden. one channel is okay, but the chip's actually designed for 3 channels. So here's another routine that I've created that can play 3 tones at the same time. It requires 4 bits of data, channel 1, channel 2, channel 3, and the length of that note to play all those together. I've created 2 examples here using 2 channels only and 3 channels together. Here's an example just with 2 channels, Amazing Grace. Okay, I've loaded the code onto the computer. Let's give Amazing Grace a go. And here's a great example of a 3-tone song that I've put together. It's called Funky Town. So there you have it. It sounds pretty awesome with this amplifier. Really impressed. But in my research looking into this chip, you can actually go one bit further, and there is actually a music file format called VGM. It stands for Video Game Music. And looking at this format, if it's been set up exactly for the SN76489 chip, it has the exact same bytes it needs to play the particular sound. So I had a look at GitHub, and a user by the name of Shaunti has put this Arduino package together and talks about VGM files and the VGM file format. He's also created a whole bunch of VGM files that are playable. All credits to these songs go to Shaun T. Thanks you for providing that. But if you have a look at this project, it gives you details of how to actually generate these VGM files from actual games or created software using the BBC Micro emulator. So if you've got time, I encourage you to have a look at this and give it a go yourself. Let's have a closer look at this VGM file format. There's excellent documentation on the VGM file specification, and in summary it has a header, and scrolling down it talks about the header information, but then the data information. So once you pass the header, you have commands, and the commands that I'm interested in is the 50 command. The next value is the value to send to the chip, the SN76489. And then there's the delay commands, which are, if you scroll down, 61, the next 2 bytes you need to wait n samples, and 66 means the end of the data. Let's have a closer look at a VGM file. Here's one of the song files that Shaunti has provided, Ghostbusters VGM. If you have a look, the first 40 hex bytes is header, and then we've got the data command. So 50 is saying that the next byte needs to be sent directly to the chip, which is 9F. Now I know what 9F is. That means mute channel 1 or tone 0. And then 61 is the delay, and it wants to set a delay to 0013. Remember, this is a 2-byte format. You reverse the bytes, and then do another 50. Looks like 9F again to silence it, and for another delay, OA61. And that's it. But first, we need to play this thing, and we need to send it from my computer to my Z80 single board computer. So there's a couple ways I can do this, using the Z80 SIO, using a circular buffer, but I didn't get around to that. I kind of cheated. I've created a C++ file that does it. Let's have a look at that. So the C++ file essentially opens the file and stores all the data in a variable called data. Then it skips the first 40 bytes and then looks at each byte. If it finds a 50 in hex, then all it does is, using a serial library, it just writes the character out to the serial port, it writes the next character out. The rest of the code in this case statement is just to make it look fancy on the screen, a progressive bar. If it finds a 61, which is a delay, wait n samples, all it does is, for the next 2 bits of data, it will do a delay. And the delay is basically a sleep routine based on the number of samples. It asks for the delay, it will sleep. All right, enough of the code. Let's now get some music happening on this chip. Okay, so here is the final configuration with the full setup of this board. Got the sound chip, amplifier, and now the LM3915 audio to LED chip with a 10 bar LED display. You can replace this with 10 LEDs. Also options here to do dot or bar mode. And if you don't have the amplifier connected, then you can connect this up to an external audio source. I've also now got it connected to a more powerful speaker, one of these portable Bluetooth speakers. Okay, so let's see how this board works with the full setup. Okay, here's the setup. Stream from the computer via USB to serial port connection to the tech. Tech is connected to the soundboard. Hit go on the tech. It's now waiting for the stream to come, and hit play. So this has been a really interesting project. This little chip here, the SN76489, from playing simple notes to playing awesome sounds, it's quite powerful. It's been a really fun project to do. If you'd like to continue this project, you can download all the code. It also has the Gerber file for the board. You can also purchase the board on PCBWay. Some further improvements could be to stream the data via a Z80 SIO, which I have here. I just haven't had time to develop that yet, and using a circular buffer to manage the timing of the data sent to the chip. So now it's your turn to get your hands on this chip and make some beautiful music. So on that note, I'll see you next time.